Hola, hola.
Yeah, we'll just do this one. Super, and I'll pocket this. I'll take this one and go back. Don't leave it there. Hello, everybody, and welcome to our first talk, our keynote speaker. Our first talk is David Cuartielles. You may know him as one of the original founders of Arduino. At the time, he was big into the physical computing thing, and I don't think it's an exaggeration to say that the Arduino actually created a revolution in the way people programmed physical devices in our community. It used to be like only a hyper fringe of nerds doing microcontroller stuff, and the Arduino really mainstreamed that. Since then, he's been working on all of this kind of design around microcontroller stuff. He's now a professor up in Malmö, Sweden, working on design. And like the rest of us, he's started to think about the environment a little bit. And so today's talk is going to be about how to make our projects more environmentally friendly and envisioning a possibly radical future of significantly more environmental friendliness. So please join me in welcoming to the Hackaday Europe stage, David Cuartielles.
Hello, hey everybody. I'm really honored to be here. I'm really glad to see there are so many people wearing double XL. You know, I ran out of t-shirts, so I had to get a t-shirt size M, thanks to you. They told me you really like camping with these t-shirts, as to make the tent with them. Anyway, so I'm head of the Interaction Design Masters at Malmö University. It's the oldest Interaction Design Masters in the world. It's an honor to do this job. It's also really hard. This year, for example, I had 200 applicants in the first round for only 22 seats. And evaluating 200 applicants in a fair way is super, super hard. I'm also one of the founders of Arduino. And today I will talk about bio-based electronics. In the second half of my talk, I will spend the first half of my talk bragging about stuff, because you people don't necessarily know me. So, but first I want to throw my respects to all of the other speakers. I'm really glad to be here for someone with math, which course I took, and I never got a chance to manufacture anything. You know me, I'm in the Discord channel still. And Bunny, who actually many years me a couple of his clocks so that my daughter could have a clock at her mom's place and at my place as well. So it's, you can't imagine to which extent this community makes my life a lot better. So thank you, everybody. After this, why am I here? Well, I'm responsible for this shape. This is my freaking idea. So blame me, not anybody else. Not only that, you can find my name in the original bootloader, who is an evolution of Dr. Eric Ling's Chip 45 original bootloader design, together with my colleague Dave Mellis. And we had like a hacking competition to see who was the cleverest. So we were like making additions and hacking on each other's code for a while. This is just one extra excerpt of the code, but it went on for quite a while. And I'm also the person who put together the Arduino forum and kept the website running from 0 users to 5 million users. So that's definitely my credit. That's on my shoulders is my legacy, and also very problematic sometimes. But then people made things out of this. And I want to make shout out to Arduboy, one of the nicest projects I've seen done on Arduino's software technology, or Madame Barbara's like stitching machine, which is a completely open source sock stitching machine. If you want to have 300 meters of sock made very quickly, this is your design. Or Professor Simon Nidenthal, one of my colleagues in Malmö, who was creating games to re-educate people's sense of smell during the pandemic. This is in my kitchen at home. We were like prototyping with like Unity and RFID tags and scents. The funny thing is, like, I didn't really get COVID. I never lost my sense of smell. I just can't distinguish between smells. And Simon tried to teach me, and you know, I just can't. Like cinnamon and cardamom are the same thing to me, you know. But Arduino is used in like real life settings. For example, many of the SAS land vehicles, they are geofenced using Arduino boards and GPS boards. So if you try to write it out of the landing line will probably block, and Arduino will be responsible for shutting down the power. And there is, of course, all sorts of research missions that use Arduino boards. Here's a PhD student from Luleå University in Sweden who is trying a fuel system for rockets using the European Space Agency zero-gravity plane. So it's, again, dealing with an Arduino Mega some years ago. So Arduino has been traveling all over the world. It's been using a lot of different things. And that takes us to the present. In the present, Arduino is something like this. Many of you have seen the evolution towards new boards. Many of you have been probably using the documentation system. I'm actually responsible for the new documentation system, or I was, until 2 years ago. I helped redesigning everything, so we went from a fantastic, I think this microphone's power goes up and down, guys. Anyway, I was responsible for going from a wiki that was constantly hacked by Russian hackers to announce beautiful porn sites, or Bitcoiners, which were heavily attacked by our hackers at Arduino for like putting like a mining machine in our servers. So now we have everything on GitHub. You can contribute through GitHub. Yes, register. You can propose changes and tell us we make misspelling errors, as many as you want, and so on and so forth. And everything is rendered, and the whole Arduino website is plain HTML. So go hack it if you can. You know, you have to hack Cloudflare. So it's not on us. And also the Arduino IDE, who is now done has a new life as TypeScript, which allowed us to collaborate with the Eclipse Foundation. Sorry, I'm a bit slow right now. It's like 4 hours, so. And of course, there is thousands of contributors into the Arduino ecosystem. And one thing we did is to make sure that everybody's licenses were properly registered. So when you're making a project, you know, oh, I have a piece of code that is BSD and a piece of code that is LGPL. How do those match each other? And what should I change for my project to be whatever license you want to have? Like, we really don't want to stop people of making projects where they want to be rich and they want to hide the code from their customers. That's really their thing. You know, but you need to know where the license stands if you're going to do that. And of course, we integrated the latest technologies. And I guess you don't know this, but we also make computers that could be upgraded over the air. So Arduino has gone pretty far now. We have, for example, these computers that can use Foundries, and you can use Docker to create your containers and then say, oh, I want this AI now to run on this board that is set on this place on that mountain, and send it over 5G or whatever and update the software, you know. And just, if you're looking pins, it has 160 pins on the back, because I guess when you're looking at this, you're like, okay, but where can I put my LED? Okay, you have 160 LEDs, don't worry. You can put as many blinking things as you want to on them. Oh yeah, you see this funded by the European Union. I think this is relevant because I'm going to be talking a lot about European-funded research today. So this particular board was created as part of the Decode project. You know, in Europe, we have these crazy acronyms for projects. Decode stands for Decentralized Citizens Own Data Ecosystem. And the idea was that people should be allowed to collect data in their balcony and then share it with a cloud service, but signing it with blockchain so that they would know their data was theirs. And that we needed to have an 8-core computer that was the size of a thumb. So that's what they paid us for, you know, to design this computer. So we spent 3 years to do this. And it's great. Now it's the core. This gave birth to Arduino Professional, like a whole new line of boards that I use in the industry. Oh yeah. And if you like religion, read my book. Thank you. But then, nowadays, where I work is with research. I'm really concerned about how technology has an effect in society and how actually technology can also enhance society. So I wrote this paper together with Cesar Garcia, a colleague of mine, where we analyzed the evolution in Europe from the hack labs that were typically extremely left-wing, and they were born in Italy and Spain, all the way to after-school robotic educations. And we mapped the approach of all of these different spaces, and we defined 2 different terms, commodification and commoditization, to make a map of how these spaces have evolved. And we realized that the more you remove politics from technology, the more parents want their kids to learn to be hackers, which is funny, right? Because hackerism is born as a way to criticize society, and now everybody wants their kids to be hackers because they think they will become Mark Zuckerberg, which is okay, insert some PIB in there. So I think interesting. Really, this microphone is killing me. I want to recommend this book in which I didn't write anything, but this book for me was transformational. Like the moment if you want to have or build a critique about how computers work and what computers are doing to us and the environment in general, this book is having a collection of real good pearls. Every single chapter is fantastic. There is chapter number 1 is called "The Cloud is a Factory," where it explains that the cloud, in the time this book was written 3 years ago, was in as much energy as the whole country of Denmark, right? It has another chapter, which being in Germany is really great. It talks about how IBM, when arriving to Germany, helped in destroying the power that the unions had at the factories in Germany by introducing the idea of the company as your family. So it's very interesting how you can build a reflection about how technology and the companies that build technology can transform society for good, but also for bad. So to me, this book really marked a before and after. I realized we were putting out boards all the time. We're putting out millions of boards. Arduino has probably put out 40 million of boards, and our designs, especially the open source family of boards, are copied massively. So we have no understanding on how many boards there are out there right now. We have no idea. And the implications of that are huge. I mean, the good things with microcontroller boards is that they are very long-lasting. They're very durable, and they're designed to last 40 years. So we are sure that at least what we're doing, if people know how to use them, will be kept in circulation all the time. But still, things will eventually break, and what happens then? So I came to talk about the future. This was my whole introduction until this point. Let me drink some German beer. From Hamburg. So, yeah. I'm typically associated with these two entities, Malmö University and Arduino, but currently I'm also one of the founders of the European Open Source Academy, and I'm working in 2 different research projects. One is the impossible to say REX concept project, and the idea of this project, by the way, the logo is in progress, so I'm just showing here you're welcome to post it, but we are completely unsure whether this represents what we want to be. But this project is looking at building a European infrastructure to do citizen science. So we want to build a decentralized system for people to share research projects so that you can involve other people to help you realize what you want. And we are partners. This is to build a concept of an infrastructure that should last 30 years. So this is a very conceptual and abstract project. On the other hand, this is a project I really come to talk about, which is Desire for EU. Or if you're French, I guess it will be Desire for EU. And the acronym is even better, is Designing and Recycling Sustainable Electronic Boards for a European Circular Economy. So the idea is to look at how we can affect the electronics market in order to make electronic circuit boards that could somehow become part of a circular economy. And this can be done in multiple ways. One way could be make sure that boards have multiple uses and that we find a way to dispose the remains. So let's go into the future. In the year 2525, we'll have figured out how to get the electronics into a bioreactor on our desktop, and then we will get beautiful bananas out of it that we can eat, okay? This is alchemy 101, you know? Just to give you some data, nowadays, in Europe, the only electronics that are really recycled are the motherboards of mobile phones. So there's a company in Belgium that does this because of the precious metals on the boards. But everything else becomes more or less landfill. So in the future, we have figured out how to fully recycle electronic components. And looking a bit at greenwashing made by some companies, we have the Daisy robot from Apple that is supposed to be desoldering all of the components of electronic boards. So we know this is possible. We've seen this happening. So we know it's possible to not just desolder, but reclassify and reuse electronic components. I mean, all of you at some point desolder something and plug it somewhere else, okay? The problem here is not doing it yourself on your bench, is to think about scale. And we have also in the future figured out how to dispose biodegradable parts fast, which means we have made machines where we can put in electronic boards through a bio process, for example, microorganisms eating the plastic, It spits out biofuel that we can use in our vehicles or the heating or whatever, and balls of copper that we can recycle. Copper, as you know, is a very useful material. It's very easy to recycle it in a hygienic way with a high level of purity. We're talking over 96% purity. So it's perfectly reusable for electronics after being recycled from electronics. The thing we're lacking today is the way to recycle this copper from electronics. We could, I wouldn't say stop mining if we did it right, but we could really reduce mining by a lot if we knew how to recycle the copper from electronics. So we need to revise the materials that are needed to manufacture circuit boards. This is really the goal of the spread I'm talking about. So let's go back to today. Today, we're dealing with this. We have set some goals, and we try to follow them in order to figure out how to make a better society. The question is, how can we reconcile the SDGs with the electronics industry? Electronics industry is about machines that make machines. And SDGs are about humans making a better world. So we need to figure out how to make those two things reconcile. If we look at, for example, Germany, there is 12 tons of CO2 per person and year that are delivered in Germany. In order to be at a climate-friendly level, there should be 2. So we should cut by 6, a factor of 6. A big portion of this is the manufacturing and use of electronic devices, and also eating bratwurst, but let's not talk about that. Let's do one thing at a time. First we can do electronics, and then we can do bratwurst, okay? And we have to avoid greenwashing. This is a really, really a big problem. It's very easy. People very quickly jump on things, and they say, oh, we're doing a better world, but what we're doing for real is a marketing campaign so that you can buy more of the non-good stuff. So if we do an academic analysis of papers that are dedicated to the concept of biodegradable electronics, we see an ongoing amount of material being produced. Like research is really flourishing. There is more and more things coming out. And this community, I think, has the opportunity of tackling this research and do something interesting. This systemic review was stopped in the middle of last year. It's not like 2024 had less papers. It's like it stopped in the middle of 2024. So you can see the growth. But there's hundreds of processes that are involved in making one digital device. So I'm going to show you some pictures of the Arduino factories so that you can see how many things need to be changed in order to make PCBs that can be made of biomaterials. First of all, let's take an eagle-eye view of where we manufacture our PCBs. PCBs for Arduino are manufactured by an Italian company called Alba PCB that is in Venice. It's a classic CNC process. So this machine drills holes on the PCB in order to make vias and holding holes for the circuits. This is a pretty long line. The line in the back with the yellow cranes is the one that carries the boards into and out of acid all the time so that the things are etched. The line in front is a washing line. So a circuit has to be put in here and it's washed multiple times. It uses a lot of water in order to make sure you remove all of the acid leftovers and you can add other materials on top in order to do a second layer of etching or the paint or whatever other process you have to do. There is a lot of remaining materials when you design a circuit board. I love this picture. The real usable part of this circuit board is the horizontal lines. It's a sensor, okay? I cannot tell you which sensor it is. I cannot tell you which company is doing it. I will be breaching some NDA, so but I can show you the picture. But what really matters for me in this picture is the hexagons on top. So those hexagons are designed so that when you're etching the circuit in the acid, the amount of copper on every part of the circuit is kind of like equivalent, so that the etching is not affecting your circuit in a worse way, in a bad way. So when you manufacture things, you actually have to add things to the panel to make sure that the etching is not too aggressive with your layers. I mean, when I realized about this, my head exploded, you know. So in order to make my very tiny 2 times 2 centimeter circuit, I need to make a 2 centimeters ring around it of materials that I'm going to waste, just like that. This box, we have Andrea who's super smiling. This box is an oven that is put for several hours at 100 degrees and is used to cook the silk on top of the circuit. So when you make your circuit, it needs to sit there for 100 hours to dry the paint. to make sure it's cooked properly, and the layer that you put on top is really protecting the electronics. So there is over 70 processes that have to be done sequentially to make a single PCB, to make a properly industrial IPC, fire retardant, etc., PCB. And of course, there is testing. I mean, this machine is mesmerizing. It's electrical testing, and it has 4 arms on top and 4 arms on the bottom, and it's checking every connection on a circuit to make sure there's no short circuits. So all Arduino boards go through this. I will make a shameless plug here. This is why you have to buy original Arduino boards, period, because we make them right. And let's talk about the assembly line. Now we saw the PCB manufacturing, and let's take a look at the assembly line. This is where all Arduino boards are mounted. This is a single factory in Strambino, Italy. Here you see a whole bunch of Arduino Unos, Arduino Nanos, and so on. This is Sara. Sara Dragon is one of our supply chain managers, and she's explaining some visitors that every single circuit board has a unique QR code on it. So every board that is being manufactured can be traced back to this point. So we can, for example, determine that a batch of components used for a certain type of board is wrong, and we can call back the whole batch of boards that were manufactured with those components. This is a classic pick-and-place process. This is a testing rigs. Every single Arduino design has a test rig, which is the machine. It's called the ramen system. I just gave you a secret inner core of Arduino. You can quote me on this. So the ramen system is a set of computers that we have to test every board, because Arduino for real doesn't have any factories. So we can manufacture boards in Italy or in India or in whatever to bring our machines, and every board has to be tested in the end, and then we know the percent of the yield. So this is a slide from ST, and in this slide I want to show you where we can tackle the problem of making bio-based electronics. First, in the development, obviously we can look at components that are more respectful with the environment, but definitely in the manufacturing, we can look at processes where we can tackle the problem of using materials that aren't great. Right now, electronics are made of a material called FR4. FR4 is basically epoxy on top of glass fiber. This is extremely durable. It can withhold fire. It can be put into space shuttles. You can walk on it if you make it thick enough. PCBs are just too durable. They are too good. It's like when you have a boyfriend that is too good, there has to be something fishy with it, and it's that it never dies. And we need to get rid of PCBs at some point. So what we are proposing is design PCBs that we can get rid of. That's really the idea here. If you think that your design is going to last 10 years, then design a PCB that will last 10 years. So it's easy to recycle. So the goal is to change for a bio-based material, and we're using PLA flax, PLA flax is basically a fabric that is made of PLA, and instead of using epoxy, we're using a different material, and this thing can be strong enough to become a PCB. This is a picture, and these are the companies that are working with us to do this, make this possible. And what you see in the middle is basically the PLA flax. And if you see the weird language, it's Hungarian. If you know Hungarian, then you know what it says. I don't know. I don't know what it says. But I have a guess. But the idea is that we can do all of the processes that we do in a PCB. We just have to change the settings of the machines. The settings are super precise. These big factories, they know the reflow has to happen at 350 degrees. But you don't put everything at 350 from the beginning. You go from 0 to 160, 160 to 210, and so on and so forth. And you have your ovens at different temperatures, and so on and so forth. But new materials require new processes. First of all, PLA melts at 200 degrees. So which is the temperature you have the soldering iron at? Just think about it for a second. How do you add bolts into your 3D prints? You put the soldering iron, heat up the bolt, and push it in. Well, imagine the reflow oven at 400 degrees, and PCBs made in PLA coming in, and basically smoke coming out, because it will just evaporate. So we have to lower the temperature of soldering. This is the first step. And it's like something that is pretty mind-blowing because it's actually possible, believe it or not. The science is there. There's this paper here that is published in IEEE. If you're interested, just get the DOI and you can check it yourself, where it explains very clearly how to make a FPGA circuit and identifies the early stages, the early problems with this. So it's possible to solder as low as 120 degrees, 130 degrees, if you use the right composite for the soldering tin. So this is our goal. Our goal is to take all of the machines in the production line and lower the temperature. This has a great effect, because by lowering the temperature, you're also using less energy. So we will be saving energy. So in this graph I showed you earlier on how much energy the Germans use, we'll be cutting in different places. First of all, we will be cutting in the production. It will also be cutting in the recycling energy costs. This is another paper that you can check. Oh, sorry, go back. So this is where we are today. Today, we have Arduino Nano made on bio-based PCB material. This is fully functional with a yield of an 80-something% of Arduino Nanos that are manufactured in a lab. And we have 100%, oh, thank you for that. This means you can also do it, by the way. We have the papers out. I can show you the science, and you can copy it at any time. Arduino Uno, because it's a larger board, has 100% of a yield. So at this point, we have 2-layer boards made with bio-based materials. And if you see, I'm very careful when I say bio-based materials, because bio-based is not the same thing as biodegradable, OK? I will talk more about that soon. So right now, we have 2-layer PCBs. We have copper traces of 10 mil, copper to copper of 8 mil, H keep out of 0.4 millimeters, and so back and so forth. So the design guidelines have to change a little bit, OK? But you can still do everything else you do on normal PCBs. Can you use VGA components? Well, not today, but hopefully by the end of this project it will be possible. Because right now you can only do 2-layer PCBs, so using VGA is a bit complicated. So there's research to be done. Biodegradable means that you could potentially just put your board in a pile of compost and the substrate will disappear, okay? But not just disappearing as in degrading, because it could become microplastics, but disappearing as becoming essential materials and being absorbed, for example, by plants, because it could become a nutrient for something else. And you will end up with copper and soil. So our PCBs today are not like this. PLA flux doesn't give you this. PLA flux can actually be fully degraded in a lab. Right now we need 2 days, and our goal is to go down to 1 by the end of this project. So we want to have bioreactors where we can recycle and extract the PLA flux in full. Ideally, we should find a material that can fully degrade in nature. At the end of the day, copper doesn't really hurt nature if it's there, if you have a certain landfill that's dedicated to recycling electronic circuits. But nevertheless, we still have to make tests where we have a laser. Oh, yeah. We have to make tests in composting. This is standardized testing for biodegradable materials. So we still do compost testing, especially our colleagues in Hungary do it. This is a microscopic picture of how the material is degrading. As you see, it's a fabric, really. PLA flux is a fabric. It's not filament, OK? So it degrades as a fabric with all of the fibers and stuff. And this thing you see here is a microscopic picture we sent us of a worm eating the PLA. So ideally, we should identify modified beings that could eat this plastic. So just to close, we're formulating 2 new principles. First is the principle of cold manufacturing that refers to lowering the production temperature, with that saving energy and making things more efficiently. And a second principle that I like to call the just enough technology, where we should design systems with technology that allows us to do exactly what we want to do. We have a tendency to do things that are overpowered. So if I need to have a temperature sensor, I don't need a Linux system to just measure temperature once every 10 minutes and send it to the cloud. So I need to figure out how to make that differently, right? So our goal for 2027 is to make a 4-layer design on a bio-based material which we an Arduino Nano board with wireless and HAI. So these are already our 4-layer plans. This is already the KaiCa design that's been created right now. The space here on the right is to make an onboard antenna. So figuring out the electric properties of the material to make an onboard antenna is one of the biggest challenges in this project. Actually, there is a postdoc student from Grenoble that's working with just this. But you can expect this board to come out. So our plan is to manufacture 2,000 boards, because this is part of the project, to really tweak the whole production line and make a batch and offer it to the community to then make a huge beta testing. And that's Arduino's role, to figure out how this could work. So guys, now you know it's possible. Just do it. Start making bio-based PCBs. Thank you so much. I don't know if there's time for questions or anything. Yeah? I can take one question from there. Yeah. I don't hear anything.
Yeah? Does it work? Okay. So you mentioned this distinction between biodegradable and bio-based, and you still say that your goal by GR27 is to have these bio-based PCBs. What's the advantage of bio-based? Like plastic is bio-based. What's the purpose of having it bio-based?
I have to give you volume. Oh yeah, I have volume. So yeah, so the purpose of bio-based is that we've already working, and then we, wow. Let's just do this. So we've been working with bio-based for a while, and the application we did for the European Commission, which was bio-based. Obviously, our goal is to have biodegradable materials. Right now, it's still a challenge. There is like some other plastics that are suitable for this, but the problem is that the whole mechanization process requires some heating up and some pressing and so on. So we are unsure whether the qualities of a fully biodegradable material as of today will be able of being ready by 2027, because it takes a lot of like back and forth testing of these things. You could even claim it should be possible to do this with like simulations and so on, but there is not enough information available to, for example, train an AI to do simulations of possible materials and figure out solutions to this. So we are in a very early stage of this process. We know PLA flux works for now. We're going to stick to this for now. But if somebody discovers every other plastic between now and 2027, we will change gears very quickly and change plastic. But I want to just, like the whole idea of this talk is to explain how complex it is and why this has not been done before. And we haven't even started to talk about IPC standards, the industrial standards for manufacturing boards. So which kind of things they have to fulfill to be usable in a consumer market. So it's just yet another layer of complexity. So I always make this joke. Today I'm 50 years old. By the time I retire at 65, very likely we will still not have biodegradable PCBs. Okay, but we're setting the first stone of something that in the future will hopefully be the standard. I hope I answered your question.
How do you protect the